All right, welcome back, Chemistry 30. So we just looked at, we're short of a few bonds here, or electrons for that central one, so we tried a double bond. So you can think of this set of electrons coming down here in between the two C and the N, so making a double bond. So nitrogen has 2, 4, 6, 8. Recall a line means 2 electrons, but carbon still has 2, 4, 6. So hey, we can take another set of electrons, maybe this crew here, and simply move it so it's a double bond again. And there we go. Carbon 2, 4, 6, 8. It's good. Nitrogen 2, 4, 6, 8. So we have a complete octet for everything. And of course, hydrogen is stable when it has 2 electrons. Now earlier on I mentioned what happens if we have ions and NO plus ion. So N and O. N is group 5, O is group 6, so there's 5 and 6 electrons respectively there. So 5 and 6, but the positive there, the positive charge means that we lost an electron. So we got to subtract one from there. And that makes sense because we'll get an even number here. We get 10. If I'm looking at B, or I guess I went through this here, so going through the set here, and usually with the Lewis structure, if it's a charged ion, we put the square brackets around it with the charge. So we have 10 electrons, so join the N and the O. Alright, so we do that, and place the valence electrons around the other atoms. 2, 4, 6, 8, 2. Now, I put them around the oxygen because the oxygen is more electronegative, so start putting the electrons around it first, then the nitrogen. So 2, 4, 6, 8, 10. So the oxygen's fine, but the nitrogen only has 2, 4. It only has 4 electrons. So of course, back in the rules, if I want to make more bonds, I certainly can. So I just simply took one of these sets of electrons here and made a bond in between N and O. Won't change anything with oxygen, 2, 4, 6, 8. But now nitrogen has 2, 4, 6. So yes, you can see I'm going to have to take one more set, put it over here. And if I do that, of course my screen jumps up. But so we have 2, 4, 6, 8 for oxygen and 2, 4, 6, 8 for nitrogen. So that would be the structure there that you see for the NO that has a positive charge. C2H, we have 2 carbons and an H, so the carbons are going to be joined together with the H's all on the end. And if we count up the number that we have here in C2H, of course carbon is group 4, so it has 4 electrons. H is group 1, so it has 1 electrons. So if I have 2 carbons, 2 times 4, 4 hydrogens, 4 times 1, that gives me a total of 12. So if I just place them around originally, so put my hydrogens around 2, 4, 6, 8, I have 2 more electrons left over. And also bear in mind that I have a group in between the 2 carbons here. So join up the carbons, put the H's on the ends, 2, 4, 6, 8, 10. Then I put 11 and 12, just 1 to each carbon. So you can see that's not going to work for carbon because we have 2, 4, 6, 7. But these 2 electrons can come together and make a double bond, and then everything will work. So for this left-hand carbon, 2, 4, 6, 8. And the right-hand carbon, 2, 4, 6, 8. So it all works out. All right. Another example here. BrO3 negative. The negative, of course, means I gain an electron. So bromine, bromine, of course, is group 7 right here, group 7. Oxygen is group 6, so it has 6. So we have 1 bromine, 7. And we have 3 oxygens, 3 times 6. And then add 1 more electron for that negative charge. So add it on there. That gives me a total of 26 electrons to place around. So bromine and oxygen, if I don't have my electronegativity chart here, but bromine is less electronegative than O. O is right next to fluorine, so it's going to be the higher electronegativity. So it's going to be surrounding the bromine. So your 1 bromine with your 3 oxygens around it. Place the 26 electrons. So first of all, the bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 left over, so the rule goes, okay, place those around the central atom, 5, 6. So everything will have an octet here. Put it in square brackets with the negative, indicating that the BRO3 had gained an electron in order to achieve that. All right. A couple more here. ClO2 negative, PO43 negative. So chlorine is a group 7, oxygen's a group 6. So we have the chlorine is one of the 7s, 2 oxygens, 2 times 6. Negative means it gained 1, so add that extra electron on. So 2 times 6 is 12, so add that all up. We get 20 electrons to place around here. If I'm looking at B, phosphorus is a group 5, and oxygen is a group 6. So I have 1 phosphorus, so 1 at 5. Each oxygen is 6, 4 times 6, and I gain 3 electrons, negative 3, so add 3 electrons on. So you can see there I get a total of 32. All right, so, and the Cl is less electronegative than oxygen, so it's going to be the oxygen surrounding the Cl. So we get that, placing my 20 electrons, first of all 2 for each bond, 2, 4, 6, 8, 10, 12, 14, 16 around the outer electrons. That leaves me with 16 going to 20, that's 4 electrons left over, so place those around the central atom, 2, 4. There we go. This last one, phosphorus is less electronegative than oxygen, so the phosphorus is going to be in the middle with the oxygen surrounding it. So a bond for each one, 2, 4, 6, 8, then add up the rest that are on the other one, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And we'll see here that the phosphorus does in fact have bonds around it, 2, 4, 6, 8. Each oxygen is 2, 4, 6, 8. So it's all good. All right. Quite often when we're drawing Lewis structures, there could be more than one possibility. All of these ones, there are one possibility, but we could run into scenarios in which there are 2 or more possibilities. So there's a little rule here that we use to figure out what structure do we keep, which one is the one that will actually work. And it has to do with calculating formal charges for alternative Lewis structures. So when we draw a Lewis structure, we are describing how electrons are distributed in a molecule or polyatomic ion. In some instances, we can draw more than one Lewis structure and have all of them obey the octet rule. All these structures can be thought of as contributing to the actual arrangement of electrons in the molecule, but not all of them will contribute to the same extent. How you decide which one is the one you use? One approach is to do some bookkeeping of the valence electrons to determine the formal charge of each atom in the Lewis structure. The formal charge of any atom in a molecule is the change the atom would have if all the atoms in the molecule had the same electronegativity. That is, if each bonding electron pair in the molecule were equally shared. To calculate the formal charge, it's relatively easy. We just simply look at all the unshared or non-bonding electrons we assign to the atom on which they are found, and for any bond, single, double, or triple, half of the bonding electrons are assigned to each atom in the bond, because again, they're sharing those. So the lone pair of electrons, for example, this Cl would have 1, 2, 3, 4. It would have 4 bonded electrons, but in a bond, chlorine and oxygen, chlorine technically has one of those electrons because it's sharing. And of course, this is just going to be a bookkeeping method, as you'll see. The formal charge of each atom is calculated by subtracting the number of electrons assigned to the atom from the number of valence electrons. And you'll see that this is relatively easy when we actually go through a few examples. And we'll have to do that in the next video because we're almost out of time. So we'll see you again.